In this video, we will solve some of the problem related to the thin cylinder. Okay. Here the problem is there, and we will go one by one. What is the data he is given here? Okay. So I'll read the problem here first. A thin cylindrical shell, the thin cylindrical shell of 0.6 meter diameter. Okay. It's whatever the diameter. Is it outer diameter or inner diameter? Normally it is inner diameter, because he is given the wall thickness here. So wall thickness, if is given, then inner diameter. Okay. So we will write the data. So what the data is given here? Inner diameter. What is the notation? That is, normally we will take it as small d, even capital D we can take it. Normal d 0.6 meter. Convert all these in 1 unit, because here one unit is given mm square, and wall thickness is given mm. So we'll go all data in mm only. So convert this, that will be equal to 0.6 into 10 raised to 3 mm. Okay. So internal diameter is 0.6 meter diameter and 0.9 meter long. Okay. The length of the thin cylinder is 0.9 meter long. Therefore, L equal to 0.9 into 10 raised to 3. I will write directly in mm because he is given meter. Is subjected to an internal fluid pressure. It is subjected to an internal fluid pressure of the fluid pressure is how much? 1.2 Newton per mm square. The pressure of the fluid is 1.2 Newton per mm square. Therefore, P equal to 1.2 Newton per mm square. Also thickness, wall thickness of the cylinder is 15 millimeter. The T equal to, the thickness is 15 millimeter. T equal to 15 millimeter. He is given the internal diameter, he is given the length of the cylinder and internal fluid pressure and thickness, wall thickness of the cylinder he is given here. Okay. So calculate, you have to calculate the first one is determine the longitudinal stress. Okay. You have to calculate longitudinal stress is how much, and circumferential stress. Along with the circumference, we know that the circumferential stress is how much, and maximum shear stress. This is new. I'll explain what is that, because in the previous video I did not explain this one here. Maximum shear stress, longitudinal stress, circumferential stress, maximum shear stress. Okay. And second one is change in diameter. Whatever the change in diameter because of the fluid pressure of 1.2 Newton per mm square, how much is the change in diameter? Change in diameter is how much? He is asking. Change in diameter and length. Change in length is how much? And change in volume. Change in volume is how much? Okay. Take E equal to, that is Young's modulus is given, or modulus of elasticity, both are same. He is given 200 GPa. E equal to how much? E equal to already is given here. E equal to 200 GPa. How will convert MPa? Newton per, this is gigapascal. I want MPa. Megapascal means Newton per mm square. Both are same. MPa or Newton per mm square, both are same. That is 200 into 10 raised to 3. Okay. Just I'll write here 2 zeros are there. 2 into 10 raised to 5. 2 into 10 raised to 5 Newton per mm square. And Poisson's ratio is given 0.3. 0.3. So this is the data is given. Now we'll go for one by one. What are the calculations? So we noted down here the data here. So we'll go one by one. First one is, he is asking the longitudinal stress. Okay, longitudinal stress. What is the formula for longitudinal stress here? In the previous video we derived longitudinal stress equation, circumferential stress equation, longitudinal strain equation, circumferential strain equation. These four are the important formulae we derived, and you can check in the previous video here. Now I'll write according to that. Longitudinal stress, how we'll write? That is PD by 4T. Pressure into diameter divided by 4 times thickness. Now substitute. Pressure is how much is given here? Pressure 1.2 Newton per mm square. 1.2 Newton per mm square into diameter. Diameter is 0.6. 0.6 into 10 raised to 3 millimeter. Okay. 0.6 into 10 raised to 3 mm divided by 4 times. How much is the thickness? Thickness is the 15 millimeter. Thickness of the wall thickness is 15 millimeter is given. This is 15 millimeter. Okay. So after substitution, substitute and simplify. After substitution, you will get that the 12 Newton per mm square. This is 12 Newton per mm square. This is the longitudinal stress. Now next, what is asking after longitudinal stress? You have to calculate the circumferential stress, right? So now go for the circumferential stress. What is the formula for circumferential stress? PD by 2T, right? PD by 2T. Only the difference is here 4, here 2 is there. So now substitute the same. Pressure is how much is given? 1.2 into 1.2 Newton per mm square is given, and next one is the diameter. Diameter is 0.6 into 10 raised to 3. 0.6 into 10 raised to 3 divided by 2 times thickness is 15 millimeter. Okay. Simplify the whatever substitution here. After substitution, you will get that is 24 into 24 Newton per mm square. That will be equal to circumferential stress. First one finish, this finish, and circumferential stress finish. Now maximum shear stress developed in the cylinder. Okay, so maximum shear stress equal to normally in general sigma 1 minus sigma 2 divided by 2. Whatever the maximum stress is there divided by the minus minimum stress. Okay, so here maximum stress is which one here? The circumferential stress is 24 is there, and longitudinal stress is 12. So I can write this one as sigma c, that will be equal to sigma c minus sigma l divided by 2. Okay, how much the maximum, the circumferential stress is developed, next longitudinal stress is developed. So that minus that divided by 2. So how much you will get here? Circumferential stress is 24 Newton per mm square minus longitudinal stress is 12 Newton per mm square divided by 2. Okay, this will be 6 Newton per mm square. If you substitute and if you calculate, you will get that is maximum shear stress, that is tau max. This is how you have to calculate the maximum, total maximum shear stress developed inside the cylinder. Okay. Now these three are finished. Now we'll go for the change in diameter, change in length, and volume change. Okay. If you calculate change in diameter and change in length, we can easily calculate the change in volume. How we'll calculate the change in diameter? At what step we have to start? We know that the diameter is related to circumferential stress. Okay, and length is related to the longitudinal, right? So the change in diameter divided by original diameter is circumferential strain. We know that, right? So in the previous video you can check that the circumferential strain, whatever the strain related to circumference along the circumference, equal to change in diameter divided by original diameter, right? Now you have to you want the change in diameter. You know the diameter already is given, the 0.6 into 10 raised to 3 here. Now how will calculate the circumferential strain here, because these two are the unknown data here. Again you have, as per the Hooke's law, the previous derivation, we derived by applying the Hooke's law. Apply the same Hooke's law here in terms of circumferential stress and longitudinal stress. How we will apply here? That is strain equal to stress by E, right? That is known. That is circumferential stress divided by E minus nu into the longitudinal stress divided by E. This is the circumferential strain. Circumferential strain equal to change in diameter divided by original diameter. Okay. Now you know that circumferential stress is how much is there here? 24. 24 divided by Young's modulus, how much is given here? 2 into the E equal to 2 into 10 raised to 5 Newton per mm square. He is given in the problem, right? So substitute, that is 2 into 10 raised to 5 Newton per mm square minus nu is Poisson's ratio, he is given 0.3 in the data. Okay, substitute 0.3 into the longitudinal stress we have calculated already, it is 12 into 12 divided by 2 into 10 raised to 5 equal to change in diameter we want, and original diameter how much is given here, that is 0.6 into 10 raised to 3 millimeter, right? This is 0.6 into 10 raised to 3. So now which one is the only one is unknown data. Simplify and find out how much is the change in diameter. Therefore after simplifying, the change in diameter we will get here, that is 0.0612. 0.0612 millimeter. See here, even not the 1 millimeter, 0.1 millimeter, right? 0.0612. It is very change in the increase in diameter is this much here due to this pressure and this wall thickness, because this is required for design criteria, right? So now if I calculated change in diameter, now same way we should go for the change in length. How much change in length in the cylinder? Okay. Okay. Now, what is the formulas? The longitudinal strain. Apply the longitudinal strain. Longitudinal strain equal to change in length divided by original length. Okay. Now again for this, these are the two unknown data here. We know that length is already is given. Length is 0.9 into 10 raised to 3 millimeter is given. So for this one apply the Hooke's law. Okay, Hooke's law. That is the stress by longitudinal stress divided by E minus nu into circumferential stress divided by E. Okay, equal to change in length divided by original length. Now substitute, we know that we already calculated the longitudinal stress and the circumferential stress. Substitute these values in this equation here. So longitudinal stress is 12 minus divided by the E is the 2 into 10 raised to 5. 2 into 10 raised to 5 Newton per mm square equal to Poisson's ratio is 0.3 already is given into the circumferential stress is the 24 divided by E is 2 into 10 raised to 5. All are in Newton, all are in millimeter. Okay, equal to, we want the change in length of the cylinder divided by original length is how much? 0.9 into 10 raised to 3. 0.9 into 10 raised to 3. Okay. So now only one is unknown data, change in length. So simplify, this is minus, here minus. Okay. Minus the only one is unknown data, change in length. So from this one you just calculate the change in length equal to, you will get here 0.0216 0.0216 millimeter. See, diameter 0.0612 and length is 0.0216 millimeter. Okay, we found longitudinal stress, circumferential stress, maximum shear stress, and change in diameter and change in length. Now the remaining is total change in volume, right? We'll calculate that one. Okay. How will start the change in volume? Which equation? Again volumetric strain, right? Volumetric strain. We know that the volumetric strain equal to change in volume divided by original volume, right? We need the change in volume. Original volume is area into length. We can calculate pi d square by 4 area into length. D is also there and L is also there. This is also we can calculate. But this, you know that the how we'll calculate what is the relation between volumetric strain with the circumferential strain and the longitudinal strain I given in the previous video. We have one equation, the volumetric strain equal to 2 times circumferential strain, 2 times circumferential strain plus 1 time longitudinal strain, that is the longitudinal strain. This is the equation I given in the previous video. You just check it. Okay, apply this one in terms of, because we know that circumferential strain, because we need this one, right, to calculate. So now I'll substitute here 2 times circumferential strain plus 1 time longitudinal strain equal to change in volume divided by original volume. Okay, now substitute. So how will go here? That is 2. Circumferential strain is what? In terms of circumferential stress, that is circumferential stress divided by E minus nu into circumferential longitudinal strain, longitudinal stress divided by E, right? This is total already before we calculated here, plus this is plus. Now the longitudinal strain is, how much is there? Longitudinal strain is the longitudinal stress divided by E minus nu into circumferential stress divided by E, right, equal to change in volume divided by original volume. Now we know that circumferential stress, we know that longitudinal stress, we know E, we know the Poisson's ratio, everything we know, volume also we know. Substitute and calculate the change in volume. I'll substitute here, just check here. Now 2 times left side, 2 times, what is the circumferential stress here? That is 24 divided by E is 2 into 10 raised to 5 minus Poisson's ratio is 0.3 into longitudinal stress is 12 divided by 2 into 10 raised to 5 E. Okay, plus, now come to the longitudinal stress. Longitudinal stress is 12 divided by 2 into 10 raised to 5 minus Poisson's ratio is 0.3 into circumferential stress. Circumferential stress is the 24 divided by 2 into 10 raised to 5. This is the left side portion, equal to, we want the change in volume divided by original volume is area into length, pi d square by 4 into length, right? I'll substitute here directly d and l value. Okay, what is the pi into divided by pi into diameter is 0.6 into 10 raised to 3, 0.6 into 10 raised to 3 pi d square by 4 into length is how much? Length is 0.9 into 10 raised to 3, 0.9 into 10 raised to 3. So now, left side is this much, this one, and right side is, just I erase here to remove the confusion here. Okay, now this is the equation, right? The left side is this one and right side is this one here. This is equal to this, which only one is variable, change in volume. Okay, simplify and calculate. You will find finally the change in volume equal to 58 into 10 raised to 3. 58 into 10 raised to 3 mm cube. Okay, this is how, now this is also finished. So change in length we calculated in terms of minute, it is very less. Change in diameter also very less, and change in volume overall it is 58 into 10 raised to 3 mm cube. Okay, this is how you have to apply all the formulae, whatever previously the two three videos I explained, I derived the equations, all the formulae I applied here. You can use this problem for your understanding purpose. Okay.